Today's video is sponsored by Delete Me. Although we have dramatically increased the amount of power generated by wind and solar over the last few decades, there is still one inescapable reality which still exists. The sun goes down every night and remains off limits for approximately 12 hours every day, and cloud cover can reduce solar output to a fraction. Even in the windiest environments, there can be lulls which last from hours to days or more at a time, which will also coincide with solar variability every day. So how can we rely upon renewables like wind and solar for 100% green energy supply? Well, we can't. We can have batteries to help store the excess energy, but that's still a long way from being ideal. What we really need is energy that is created all day, every day, regardless of whether the sun is shining or the wind is blowing. With the move away from fossil fuels, there are just a few options left for energy generation that can be relied upon to run on a continuous basis. These are hydroelectric and geothermal power, and hopefully in the future, tidal power. But these are only available in certain parts of the world. The other alternative is nuclear power, and hopefully one day nuclear fusion, if and when it ever becomes a reality. So up until then, we'll have to make do with nuclear fission, the power that created the atomic bomb and has powered every single nuclear power station since the 1950s. Back then it was thought that by the end of the 20th century we would be able to run the entire world on nuclear. The fear was that we might not have enough uranium to go around. But as time went by, we began to realise that the vision of a nuclear-powered world would be far more difficult than anyone imagined, and with accidents like 3 Mile Island, Chernobyl and Fukushima, nuclear power has been in decline since the 1980s. It's only in the last decade that it's made a resurgence, with the fuel shocks of the Ukrainian war escalating it even more. And then there is the issue that nuclear power is inextricably linked with the production of nuclear weapons. In fact, the only way to create the plutonium from the bomb that was dropped on Nagasaki in 1945 was in a nuclear reactor, and the technology used to make nuclear power stations can, with a little modification, produce plutonium for weapons. So there was a great deal of political support for the uranium cycle reactors, but that wasn't the only way to create electrical power from nuclear fission. It was thought in the 1950s that we might actually run out of all the uranium for the nuclear power plants that would be required in the future, and that was the basis for another experiment using an even more abundant supply of nuclear material, thorium, and a different type of reactor, one that didn't rely upon water to keep it cool enough so that it didn't overheat and cause a meltdown or China syndrome. Molten salt reactors promise greater safety and efficiency over current designs, but there are crucial issues surrounding the corrosiveness of salt and the metals used to make them, which up until now have limited their development. Now this reminds me of today's sponsor, Delete Me, because they deal with a problem which also shouldn't really exist, and that is the privacy of all the data held on us by big tech. With the digital tracking of all our movements online and the digitization of our personal data, a large and highly profitable ecosystem has developed to tie the two together to serve us with personalized ads, video feeds, and news based on what they think we want to see, hear, and read. At the bottom of all this are data brokers, companies that buy and sell data to anyone who wants it, and this is where the problem lies. This can include emails, names, current and past addresses, phone numbers, age, occupation, and much, much more. If anyone can buy data about you, it can become a security or even a personal safety risk if you work in places like the government, military, civil services, or you have a high profile. While you can request these companies delete the data they hold on you, with over 750 data brokers around the world, where do you start? And this is where Delete Me comes in. Delete Me has been helping normal people like you and I get their personal information removed from data brokers since 2010 in the US, UK, and Europe. Delete Me is simple to use. You just select the plan you want, fill in the online application, and Delete Me will contact the hundreds of data brokers to remove you from their lists. You receive regular privacy reports that show how much data was found, where it was found, and where it was removed from. You can do this for yourself or for your family, and if you use the joindeleteme.com/droid link in the description below, or scan the QR code next to me today, you'll get a 20% discount. As with many things, the military saw a use for this new wonder fuel before any commercial power generation was thought about. In 1946, the US Army Forces formally studied the possibility of using a nuclear reactor to power supersonic bombers with effectively an unlimited range. To do this, they would need a small, compact nuclear reactor that relied upon liquid sodium metal as the heat transfer agent and coolant instead of water. In 1954, the ARE, or the Aircraft Reactor Experiment, was built and tested for 4 days at the Oak Ridge National Laboratory. This was a prototype for a 350 megawatt beryllium oxide moderated circulating fuel aircraft reactor. The ARE had an operational targeted life of 1,000 hours and a full power output of 3 megawatts. The fuel and coolant was a mixture of sodium fluoride, zirconium fluoride, and the nuclear fuel uranium fluoride. This flowed through a series of tubes in the reactor core and was surrounded by an Inconel shell. The design temperature of the liquid fuel mixture was 820 degrees Celsius, and 170 litres of this molten salt and fuel flowed through the reactor at a rate of 570 litres per minute at a pressure of 50 psi. The advantage of a molten salt reactor is that the fuel is already in a molten state in the salt, and if it gets too hot, the fuel-salt mixture expands out of the reactor and the reactivity reduces. This negative temperature coefficient means that it's impossible for a meltdown to occur. Unlike in a conventional water-cooled reactor, if there is a loss of coolant or if the water flashes to steam and it splits into hydrogen and oxygen, an explosion can occur, which is what happened at Chernobyl and Fukushima. Although the ARE only ran for 4 days at a maximum of 2.5 megawatts of thermal power, it was sufficient enough for a follow-on reactor to be built in the 1960s, with the intention of paving the way to a thorium molten salt reactor, which would produce much less radioactive waste and less in the way of weapons-grade material. The MSRE, or Molten Salt Reactor Experiment, was also built at Oak Ridge National Laboratory, going critical in 1965 and running up until 1969, and it was to simulate a liquid thorium reactor. As the salt-fuel mix flowed through the reactor, it would be heated up to 650 degrees C by the reaction. This then flowed through air-cooled radiators. There was no electrical generation capabilities, and it did this at full power for the equivalent of 1.5 years. Although it was operational for 4 years, there were lots of time when it was not functional due to faults and external issues. This was, after all, the first experimental molten salt reactor, and the material sciences were still in their infancy. The piping, core vat, and structural components were made from hastelloy N, a low chromium nickel molybdenum alloy. The pyrolytic graphite core also served as the moderator, which slowed the neutrons created by the reaction to make them more likely to react with the fuel and increase its reactivity. If the salt got too hot, it would expand and reduce the amount of fuel in the core and therefore reduce the reactivity. So it was not possible to induce a meltdown. This is the core primary safety feature of a molten salt reactor, and the one which differentiates it from a traditional water-cooled reactor. However, after the reactor was shut down, there was found to be a problem with the corrosiveness of the salt and the hastelloy alloy which was used to create the structure. As anyone who lives near the sea knows, salt and metal don't go together well, although some types of metals are much less susceptible to salt corrosion, such as nickel. The problem inside a reactor is, not only is there salt, it's at a high temperature, which increases its corrosiveness. And there is also neutron radiation, which causes embrittlement of metal. Combine all three, and even the best alloys at the time would have had a short lifespan. While this was enough for the experimental reactor to last 4 years, in a commercial reactor it might be expected to run for 40 to 60 years. And this became the Achilles heel of the molten salt reactors. If the metals that make up the reactor start to fail after maybe 5 to 10 years, it would not make for a viable commercial reactor. And although it would have been possible to create better alloys, the whole molten salt reactor project was shut down in favour of more well-known and more scalable uranium cycle reactors and their ability to create weapons-grade plutonium. For decades afterwards, some people have proposed restarting the thorium molten salt reactor programs around the world, but it wasn't until the 2000s that interest increased enough for governments to start looking at creating new thorium reactor projects. Material sciences have also increased dramatically since the 1960s, so the alloys available today are also much more capable. And at MIT, a recent research program has discovered how the salt and high radiation levels were affecting the original materials. Metals are made up of grains, and within the grains are the crystalline structures of atoms. But at the boundaries of the grains, it was found that salt finds atomic level openings in the solid, seeps in and dissolves salt-soluble atoms, pulling them out and leaving a gap in the material, a spot where the material is now weak, and further cracks can form, allowing in more salt until the material fails. High-energy neutrons found in reactors also affect the crystalline structure of some atoms, causing voids and swellings to occur and making them weaker and become brittle. The combination of salt and radiation is therefore thought to be the worst of all worlds. However, the team at MIT have discovered that the radiation also accelerates the salt atoms, and instead of concentrating in the voids between the grains, it is dispersed more throughout the entire material, and in effect slows down the salt reaction. Although the research has to be verified by other research teams, they discovered that the proportion of chromium, which is salt-soluble, to nickel, and the amount of radiation could make a significant difference to the corrosion that occurred, and knowing this, new materials could be formulated that will be much more corrosion resistant and eliminating one of the biggest obstacles to molten salt reactors. China has already taken the lead and created the first thorium molten salt reactor and showed that this 2 megawatt unit could power up without a problem. They have also achieved another first by being able to fully reload it with fuel whilst it was still running. The US, Russia, Europe and several other countries are building their own thorium salt reactors, and several of them are expected to come online by the 2030s. Their contained design also makes them ideal for small modular reactors that are currently being proposed to power towns or cities in remote areas and to back up for when solar and wind are not available. In all, it might not be the panacea that fusion promises, but it will go a long way to make nuclear a much more acceptable form of power, where renewables are not a viable option. So thanks for watching, and don't forget to thumbs up, share and subscribe, and a big thanks go to all of our patrons for their ongoing support.